There's a question on a text problem that gives a very interesting application of this idea of asymptotes. We have a cylinder, and we say that the volume of the cylinder is constant, but the cylinder can be stretched to different lengths and diameters without changing the volume. Well, if we're not going to change the volume of the cylinder, and we have a cylinder, let's say here, a relatively short fat cylinder whose radius is r and whose height is h. So it's r units radius, h units height. If we change the radius to 1/2 r, what has to happen to the height? A lot of people would say, well, half the radius, you're going to have twice the height. That doesn't work. If you think about the little tiny cubes that make up this cylinder, using that cube model, what has to happen when you shrink the radius to 1/2 r? The cubes have to shrink in this direction, and they have to shrink in this direction also, this direction and this direction. So the cubes become half as wide and half as deep, let's say. In order to make them have the same volume, we're going to have to stretch them in this direction so they become 4 times as high. So the height of this whole figure is going to have to become 4 times as great. We can see that by thinking of tiny cubes. We can see that by looking at the formula for the volume. The volume is pi r squared h. Now that should equal the volume we get if we reduce r to r over 2. If we reduce r to r over 2, we got pi times r over 2 quantity squared times whatever the height is. Well, that height is going to have to be 4h, because this 2 is going to get squared. In order to take care of that and get pi r squared h, we're going to have a 4 in front of h. In general, if we reduce r by a factor k so that r becomes r divided by k, then h had better become k squared h. The height had better become k squared times as great if the radius becomes k times less. If we do a little bit of algebra, we start with the idea that the volume is pi r squared h, which is constant. And what we're really after in this problem, the way the problem is stated, we want to see what happens to the surface area as r approaches 0. So we're going to keep making this cube skinnier and skinnier and longer. Every time it becomes twice as skinny, of course, it's going to become 4 times as long, isn't it? Okay, well, the surface area of a sphere, just looking at the formula, is 2 pi rh plus 2 pi r squared. 2 ends, each having radius r, so it gives us 2 ends with areas pi r squared each. And the sides, if you cut the cylinder and unwrap it, you're going to end up with a rectangle whose length is 2 pi r, the circumference, and whose width is the altitude h. Okay? Now, this is an expression for the surface area that involves both r and h. We want a surface area expression that involves only r. So what do? Well, we solve this equation for h. Remembering that v stays constant, v is just some number that stays constant, we get h equals v over pi r squared. Substituting that value of h into this expression for the surface area, we substitute it here. We don't have to substitute anything here, and simplify. We see that the surface area is 2v over r plus 2 pi r squared. What happens as r approaches 0? Well, as r approaches 0, 2 pi r squared approaches 0. The areas of the ends are going to approach 0. They're going to shrink down to nothing. However, the area of those sides is going to be 2v over r, and as r approaches 0, that's going to approach infinity. So we have the counterintuitive notion that as we stretch these cylinders out, draw them out thinner and thinner, the surface area approaches infinity.